Ever feel like you're just staring at a spreadsheet that, I don't know, looks more like alphabet soup than actual information?
Hmm.
If you've ever wished you had, like, a secret decoder ring for data, this deep dive is definitely for you. We're diving into descriptive statistics. These are the tools that help us take that jumbled mess of numbers and actually make some sense of it.
Exactly. Yeah, today we're going to focus on some of the foundational concepts in descriptive statistics, the kind that are, well, absolutely crucial in the world of data science. We'll be looking at different ways to summarize and, understand data using these pretty powerful measures.
Okay, so our mission today is to give you a clear understanding of these fundamental tools, things like the mean, median, variance, standard deviation, all that good stuff. We want to go beyond just the definitions, right?
Yeah.
And really explain why they matter in data science and, maybe more importantly, when you should actually be reaching for each one. And we'll also tackle a question that's probably popped into many people's minds. Why do we use the mean for calculating variance instead of the median? Okay, let's get started. Let's unpack the mean first. What exactly is it, and why is it such a kind of cornerstone of statistics?
Right. So the mean, the often just called the arithmetic average, is basically calculated by summing up all the values in your data set and then dividing by the total number of values. Simple enough. Its importance really comes from the fact that it gives you a central kind of representative value for your data, almost like the equilibrium point, you could say. It's a fundamental building block for so many other statistical techniques, and it's essential when you want to compare, say, different sets of data. Plus, it serves as the baseline for understanding how spread out your data is, which naturally leads us to things like variance and standard deviation. It even plays a role in forecasting. Think of it maybe as the center of gravity, the point around which all your data balances.
Center of gravity, I like that. That's a great way to visualize it. So when should we actually use the mean? When is it the right tool?
Yeah, good question. You'll typically want to use the mean when your data is relatively symmetrical, meaning it's not heavily skewed off to one side or the other, and also when it doesn't contain extreme outliers, those really wild values that could disproportionately pull the average way up or way down. It's also most appropriate for what we call interval and ratio data, that's numerical data, where the differences between the values have a clear, consistent meaning, like temperature or height.
Okay, so nice balanced data, no crazy extremes. Then the mean is your friend. When should we maybe think twice before, relying too heavily on just the mean?
Well, you definitely need to be cautious when your data is skewed, perhaps with a long tail of very high or very low values, or when you have significant outliers. In those situations, the mean can be heavily influenced, really pulled around by those extreme values, and it might not give you a truly representative picture of the typical value. And it's also not really suitable for ordinal data, data with a meaningful order, like rankings, but maybe not equal intervals or categorical data, like colors or types of fruit, where averaging just doesn't make logical sense.
Right, right. Averaging apple and orange doesn't get you much. Okay, that's clear. Symmetrical data, no crazy outliers mean is good. What about the median then? Where does that fit into the picture?
The median is simply the middle value in your data set once it's been ordered, from smallest to largest. If you have an even number of data points, it's just the average of the two middle values. Pretty straightforward. Now, the real beauty of the median, its main advantage, is that it's incredibly resistant to outliers. It's robust. Those extreme values that can really throw off the mean, they have very little impact on the median.
Ah, okay.
So this makes it a much more reliable measure of central tendency when you're dealing with skewed distributions. It also works well with ordinal data. And interestingly, comparing the median to the mean can actually give you a clue about the skewness of your data. If they're different, it suggests some skew. Plus, you can even think about non-numerical ranked lists. The median item is still just the one in the middle. Imagine like a line of people ordered by height. The median height belongs to the person smack dab in the middle, no matter how super tall or short the people at the ends are.
So if our data has some really high or low weirdos in it, the median gives us a more stable idea of the center. Is that the idea?
That's exactly it. If you suspect that extreme values might be distorting your perception of what's typical, the median is usually your go-to. It's also useful when you have ordinal, interval, or ratio data, and you specifically want a measure of central location that isn't easily swayed by those outliers.
Outliers causing trouble. Median to the rescue. Got it. Now, the mode always felt a bit like the odd one out of the central tendency measures. What's its story?
Oh, yeah, it's a bit different. The mode is simply the value, or sometimes values, that appear most frequently in your data set. You can have a data set with one mode that's unimodal, or two modes, bimodal, many modes, multimodal, or sometimes no mode at all if every value just appears once. Its primary importance, really, is that it's the only measure of central tendency that makes sense for nominal or categorical data.
Oh,
Things like survey responses of yes, no, maybe, or different categories of products. It tells you what's the most typical or popular value in your data set. And like the median, it's not affected by extreme values at all.
so if we want to know the most popular choice or the most common category, like favorite color or something, the mode is what we're looking for.
Precisely. If you're working with categorical or maybe ordinal data, and your main goal is just to identify the most frequent occurrence, the mode is the tool for the job.
And when might the mode not be all that helpful? When would it maybe mislead us?
Well, if your data set is pretty uniform, meaning all the values occur with roughly the same frequency, then there won't be a clear mode, or maybe there'll be lots of modes, which isn't very informative. Similarly, with continuous data like height again, where you have lots of different values and exact repetitions might be rare, the mode might not tell you much. And if you end up with multiple modes that are quite far apart, it can sometimes make interpretation a bit ambiguous. It might even suggest that your data actually represents several different underlying groups mixed together.
Okay, that makes sense. So mean for balanced averages, median for the sturdy middle value, and mode for the popular pick. Got the centers covered. Now let's shift gears a bit and talk about how spread out our data is. Dispersion, right? First up, the range. Seems pretty straightforward.
It is indeed. The range is definitely the simplest measure of dispersion, or spread. It's just the difference you get by subtracting the minimum value in your data set from the maximum value, max minus min. It gives you a very quick, sort of top-level estimate of how spread out the data is. It can be useful in initial data exploration, just getting a first feel. And it can help quickly identify potential outliers because an extremely high or low value will immediately widen the range quite a bit.
Right.
It also helps you understand the overall boundaries of your data. Think of it like the total width of a river, maybe, from one bank to the other. Simple and quick. But I'm guessing there are some limitations, some drawbacks to just looking at the range. Absolutely. The biggest drawback of the range is its extreme sensitivity to outliers. Just one unusually high or low value can dramatically inflate the range. And that can give you a distorted idea of the typical spread of your data. It only cares about the two endpoints. It also doesn't tell you anything about how the values are distributed between those two extremes. Are they clustered? Spread evenly. Range doesn't say. So while it can be a useful first glance, especially maybe for small data sets, it's generally not considered a very robust measure for more detailed analysis, particularly if you suspect outliers or have skewed data.
Okay, so range gives us the full wingspan, the absolute maximum spread, but not much detail inside. That's where the interquartile range, or IQR, comes in, right?
Does it give a better picture?
Exactly. The IQR offers a much more robust way to look at the spread. It focuses on the variability within the middle 50% of your data. To calculate it, you first find the quartiles. Q1, the first quartile, is the value below which 25% of your data lies. And Q3, the third quartile, is the value below which 75% lies.
Then you simply subtract Q1 from Q3. IQR equals Q3 Q1. This gives you the range or the spread of the central half of your data, effectively ignoring any extreme values in the outer 25% on either end.
Ah, so it cuts off the extremes.
Precisely. It's fantastic for understanding the core distribution of your data and for identifying potential anomalies or outliers, because those extreme values just won't influence the IQR. It's also a key component of box plots, which are a great way to visualize this stuff. Imagine a class's test scores again. The IQR would represent the range of scores for the middle half of the students, giving you a good sense of the typical performance, regardless of a few exceptionally high or low scores way out there.
So the IQR is much more resilient to those pesky outliers we keep talking about?
Exactly. Much more resilient. You'd want to use the IQR when you know or suspect your data is skewed or contains outliers, or maybe when you're working with distributions that aren't, perfectly normal or bell-shaped. It provides a much more stable measure of how spread out the bulk, the main body of your data is in those situations.
Makes sense. Range is the full span, IQR is the more reliable middle section. Okay, now we're getting into variance and standard deviation. These always seem to go hand in hand. Let's start with variance. What's it really telling us about our data?
Right, variance. It's a measure of how spread out your data points are, specifically around the mean. That link to the mean is crucial. Mathematically, it's the average of the squared differences between each data point and the mean. So you see how far each point is from the mean, you square that distance, and then you average all those squared distances.
Squared differences, okay.
Yeah. So a low variance tells you that the data points tend to be very close to the mean. It indicates high consistency, maybe high predictability. Conversely, a high variance indicates that the data points are more scattered, further away from the mean, suggesting greater variability, more spread. Variance is a really fundamental concept in statistics. It's used in tons of other calculations, standard deviation, obviously, but also confidence intervals, hypothesis testing, regression analysis. It can help you assess the consistency of a process, like in manufacturing, or quantify the errors in a statistical model, or even analyze the level of risk in financial data, like stock prices.
Okay, so variance is all about quantifying that spread relative to the average using those squared differences. What's the practical difference, say, between having a low variance versus a high variance in some real-world scenario?
Good question. Low variance often translates to greater stability and predictability. For example, if a manufacturing process has low variance in the size of the parts it produces, you can be pretty confident in the consistency of the output. That's usually desirable for quality control. But in other areas, like maybe the diversity of opinions in a survey, low variance might indicate a lack of a wide range of perspectives, which might not be what you want. High variance, on the other hand, suggests more volatility, less predictability. In finance, a stock with high variance in its returns is generally seen as riskier because its price fluctuates more wildly.
Okay.
But in research, maybe high variance in experimental results might suggest there are interesting factors causing that variability that need further investigation. And just one quick point to remember, we have slightly different formulas for calculating variance depending on whether you're looking at an entire population or just a sample of it. A small adjustment, but important.
That's a good reminder, that N versus N1 thing. Okay. Now, standard deviation, you said it's the square root of the variance, right? So why bother having both if one is just the square root of the other?
You're absolutely correct. Standard deviation is the square root of the variance. The key reason we use standard deviation so much is really for interpretability. See, variance is expressed in squared units of whatever you're measuring.
Right, you mentioned that earlier, points squared.
Exactly. Which can be really hard to relate back to the original data intuitively. If you're measuring test scores on a 100-point scale, the variance might be, say, 100 points squared. What does that even mean in practice?
Yeah, not much.
By taking the square root, the standard deviation brings that measure of spread back into the original units. So in our example, the standard deviation would be 10 points, the square root of 100. Now you can easily understand that. If the average test score is 75 with a standard deviation of 10, most scores typically fall within about 10 points of that average, say between 65 and 85. Much clearer.
Okay, that makes a huge difference.
It really does. Standard deviation provides a much more practical and interpretable measure of how much individual data points typically deviate or stray from the mean. It's used absolutely everywhere: statistics, data science, machine learning, finance, to quantify volatility, reliability, the degree of spread. It's also essential for understanding the properties of a normal distribution, that bell curve, the 68, 95, 99.7 rule. That's based on standard deviations.
Right, how much data falls within 1, 2, or 3 standard deviations.
Exactly. And it's fundamental in many machine learning algorithms, too, for tasks like scaling features or detecting anomalies. Think of the mean as the bullseye on a target, maybe. The standard deviation tells you, on average, how far your shots are landing from that bullseye, measured in the same units as the target distances.
That's a great analogy. So variance tells us the spread exists mathematically, but standard deviation puts that spread into a context we can actually understand and use.
That makes a lot of sense.
Yeah.
Okay, now let's talk about the shape of the data. Skewness. That sounds like it describes how lopsided our data is.
Exactly. That's a perfect way to put it. Skewness measures the asymmetry, the lopsidedness of a data distribution around its mean. If a distribution is perfectly symmetric, like that classic bell curve, it has a skewness of 0, perfectly balanced. Positive skew, which is also known as right skew, means the distribution has a long tail stretching out to the right. In this case, the mean is typically pulled higher than the median.
Okay, tail points right, mean median. Yep. And negative skew, or left skew, is the opposite. It has a long tail on the left, and the mean tends to get pulled lower than the median. Understanding skewness is really crucial because many statistical analyses actually assume that the data is roughly normally distributed, meaning not heavily skewed. Significant skewness can affect the reliability of those analyses, and, as we mentioned, it can also make the mean a less representative measure of the center. The median might be better in that case. Recognizing skewness can also help you spot potential outliers that are pulling that tail in one direction, and it might inform decisions about whether you need to maybe transform your data before applying certain statistical models. Imagine a playground slide. A normal distribution is even on both sides. Positively skewed, the long, gentle slope is on the right with a steeper drop-off on the left. Negatively skewed, it's the other way around.
Got it. Skewness tells us if our data is leaning to one side. Now, kurtosis, that sounds a bit more intense. What's
Wow.
that measuring?
Kurtosis, yeah, it measures the tailedness, or sometimes people say the peakedness of a probability distribution. In simpler terms, it tells us how likely we are to see extreme values or outliers compared to a standard normal distribution. It's about the weight in the tails.
Okay, so heavy tails or light tails?
Exactly. A mesokurtic distribution has a kurtosis similar to a normal distribution. It has moderate tails. We often define its excess kurtosis as 0. A lepokurtic distribution has positive excess kurtosis. It's characterized by heavier tails, meaning a higher probability of extreme values, and usually a sharper peak. Think leaping peak.
More outliers expected.
Right. And a platykurtic distribution has negative excess kurtosis. It has lighter tails and a flatter peak, suggesting fewer extreme values than a normal curve. Think flat like a plateau. Kurtosis is important because it gives you insight into the risk of extreme events. In finance, for example, high kurtosis, leptokurtic, might suggest a greater likelihood of large unexpected market movements, both gains and losses. Tail risk. It also helps you assess how well your data distribution fits certain statistical models that might assume a particular level of kurtosis, usually that of a normal distribution. Think about maybe hills. A mesokurtic distribution is like a standard rolling hill. A leptokurtic one has a very sharp, pointy peak. And a platykurtic one is more like a flat-topped mesa or plateau.
Okay, hills and tails. Kurtosis is about the extremes and the shape of the peak. This is all incredibly helpful for getting a really rounded picture of our data. But there's one question we haven't quite nailed down yet, and it's something I've always wondered about. Why isn't the median used in the calculation of variance or standard deviation? I mean, they both seem like measures of central tendency, right? So why the definite preference for the mean when we're talking about spread?
That's a really insightful question, and it gets to the heart of how these measures are defined and why they're useful. The answer really lies in the fundamental mathematical definition of variance and standard deviation. They are specifically defined as measures of the spread of data points around the mean. That's just their definition. And the crucial reason for this definition is a very important mathematical property. The mean is the unique value that minimizes the sum of the squared deviations of each data point from it.
Minimizes the sum of squared deviations.
Okay.
Yeah.
Yeah, think back to the formula for variance. It's essentially the average of those squared differences from the mean. Using the mean makes that sum of squares as small as possible. This property of minimizing square deviations is absolutely fundamental. It underpins many powerful statistical techniques, most notably the method of least squares, which is the foundation for linear regression and lots of other modeling.
So it's really about the math working out nicely. It's a matter of mathematical optimization and how these concepts are formally defined and used later on.
Precisely. It's deeply tied to the mathematical framework. The median, on the other hand, has a different but also useful minimizing property. The median is the value that minimizes the sum of the absolute deviations, not the squared deviations.
Absolute values versus squared values.
Exactly. So if you were to substitute the median into the variance formula instead of the mean, you would indeed get a measure of spread, but it wouldn't be variance as we conventionally define it, and it wouldn't have that crucial property of minimizing squared deviations, which is so important for things like least squares regression. It just wouldn't link up mathematically in the same way. Variance, by its very definition and its role in the broader statistical toolkit, is intrinsically linked to the mean, because the mean is the specific central point that optimizes the sum of square differences. It's like, imagine trying to find the best central meeting point for a group of people spread across the city.
Okay.
If you define best as the point that minimizes the total straight line distance everyone has to travel, it's kind of like absolute deviation and the median. But if you define best as the point that minimizes the sum of the squares of the distances everyone has to travel, maybe because travel difficulty increases sharply with distance, you might end up at a different point.
Yeah.
That's more like squared deviation in the mean. They optimize different things.
That analogy really clicks. Different ways of defining best center lead to different measures of spread around that center. So if we did actually want to measure the spread around the median, maybe because we have lots of outliers, is there a tool specifically for that?
Yes, absolutely there is. If you're specifically interested in measuring the spread of data around the median, a common and very robust measure is the mean absolute deviation, often just called MA.
MAD.
MAD calculates the average of the absolute differences between each data point and the median. So you find the median, see how far each point is from it, ignoring whether it's higher or lower, and average those absolute distances. It gives you a clear sense of the typical deviation from the median. And because it uses absolute values rather than squares, it's much less sensitive to extreme outliers than standard deviation and variance are.
Okay, so MA for understanding spread around the median, especially with outliers, and variance standard deviation for understanding spread around the mean, which connects to other math like regression. Each has its place.
It's exactly right. And it just highlights the importance, really, of choosing the right descriptive statistics based on the characteristics of your specific data and the particular questions you're trying to answer. Standard deviation and variance are incredibly powerful and widely used, especially when your data is reasonably symmetric and you need that connection to mathematical optimization methods. But MAD is a great alternative when robustness, that resistance to outliers, is a higher priority for measuring spread.
This has been a truly illuminating deep dive. Seriously helpful. We've covered so much ground here. From understanding where the center of our data lies with the mean, median, and mode, to exploring how that data is spread out using the range, the IQR, variance, and standard deviation, and even getting a handle on the shape of our data with skewness and kurtosis. And finally, we've demystified why the mean, not the median, takes center stage in the calculation of variance. That makes perfect sense now.
Yes, I think the key takeaway really is that these descriptive statistics aren't just, boring definitions. They are fundamental tools in data science, in any kind of data analysis. They provide these essential summaries of your data, helping you to really understand its central tendencies, its variability, and its overall shape. Knowing when to use each of these measures and understanding the why behind choices like using the mean for variance is absolutely crucial for effective data analysis and for drawing genuinely meaningful insights from your data.
Absolutely. So now that you listening have a better grasp of these statistical building blocks, maybe think about how they might apply to the data you encounter. Whether it's in your own field or even just stuff you see in the news or daily life, what new questions can you ask now when you see a set of numbers presented? This was just a deep dive into some of the foundational concepts, of course. There's a whole universe of statistical methods out there still waiting to be explored. What aspect of data analysis has maybe piqued your curiosity today? What do you want to dig into next?